Hi, welcome to today's talk on temperature and kinetic energy. What are we learning? We're learning about thermal equilibrium and the zeroth law of thermodynamics. We're going to learn about temperature scales, and we're going to look at the definition of temperature and relate it to kinetic energy. To understand the concept of temperature, we need an understanding of thermal contact and thermal equilibrium. Let's say we have two objects and they are in thermal contact. Let's say our thermometer here and some object A. Two objects are in thermal contact if energy can be exchanged between them. Two objects are in thermal equilibrium if they are in thermal contact and there's no net exchange of energy. So heat is the exchange of energy between two things because their temperatures are different. Now we're going to look at that in a lot more detail a little bit later. So let's go ahead and define what we mean by a thermometer. It's some sort of device or something that's calibrated to measure the temperature of an object. If we want to find out whether, say, some object A and some object B would be in thermal equilibrium if they were placed together in thermal contact, the thermometer, which we'll call object C, it's first placed in thermal contact here with object A. The thermometer is then placed in thermal contact with object B, and its reading is again recorded at equilibrium. If the two readings are the same, then A and B are in thermal equilibrium with each other. Now, if object A and object B are placed in thermal contact with each other, then there's no exchange of energy between them. So we'll summarize what we'll call the zeroth law of thermodynamics. If we have object A and object B, they are separately in thermal equilibrium with some other object C, then A and B are in thermal equilibrium with each other. What this does is it defines temperature in terms of thermal equilibrium. Thermometers, of course, are things that are used to measure the temperature of an object or system. When a thermometer is in thermal contact with a system, energy is exchanged until the thermometer and the system are in thermal equilibrium with each other. So for this to work, the thermometer has got to be much smaller than the system so that the energy that the thermometer gains or loses when it's in contact with the system doesn't really affect the energy of the system itself. So what a thermometer does is it makes use of some physical property that changes with temperature, and that physical property is something that can be calibrated to make the temperature measurable, such as the volume of a liquid, the length of a solid, pressure of a gas held at some constant volume, the volume of a gas held at constant pressure, or the electric resistance of a conductor. Also, the color of a very hot object. So this shows a type of gas thermometer. It's called a constant volume gas thermometer. What we do is we observe a variation in the pressure with temperature of some fixed volume of gas. When constant volume gas thermometer was developed, it was calibrated using ice and steam as a couple of points for calibration. So what we can do is we can take these 2 points, plot them on the graph, and draw a line and use this to calibrate it. That way we can find out any sort of unknown temperatures. What we can also do is we can extrapolate this. We can make these graphs go back all the way to where pressure is 0. That 0 point is at negative 273.15 degrees Celsius. We'll define this point as absolute 0. This is where we're going to start our Kelvin scale. Now, the size of the degrees of the Kelvin scale are the same as the size of degrees for the Celsius scale. We're just starting it at a different point. So to get from temperature in Kelvin to temperature in Celsius, all we have to do is take our temperature in Kelvin, subtract 273.15, and we get our temperature in Celsius. And on this page, we're going to relate the Celsius scale, the Fahrenheit scale, and the Kelvin scale. Mostly we can look at the ice point and steam point of water. The ice point, or the place where water freezes at 1 atmosphere, is 0 degrees Celsius. That's 32 degrees Fahrenheit, or 273.15 degrees Kelvin. Water boils at 100 degrees Celsius, or 212 degrees Fahrenheit, or we just add 273 to 100 and we get 373.15 degrees Kelvin. To go between temperature in Celsius and temperature in Fahrenheit, we take our temperature in Celsius, multiply it by 9/5, and then we add 32. Here it is, the same equation solved for the temperature in Celsius if we have the temperature in Fahrenheit. We've defined temperature already in terms of thermal equilibrium, but we can also say this, that temperature is a measure of the average molecular kinetic energy of an object. The higher the temperature, and we'll take some really good close look at this a little bit later, the higher the temperature of an object, the faster the molecules are moving. And we'll really be able to see this in our discussion of ideal gases. If we were looking at the kinetic energy of a single molecule of an ideal gas, we can find that by taking 3/2 times Boltzmann's constant, which is this here, and mostly this constant's there to get the units right, times the temperature in Kelvin. A complete derivation is in your textbook. For the sake of time, I'm going to let you look at that instead of deriving it here, just to keep the video nice and short. The kinetic energy as a function of the number of molecules, sort of the same thing, just we're taking in, capital N, the number of molecules, multiplying, just dropping that in this equation. And finally, we're going to look at the kinetic energy as a function of the number of moles, and same 3/2. In lowercase n is the number of moles, and R is a different constant that gets us to the correct units. All right, let's summarize what we know so far. First, we have the 0th law of thermodynamics. If you have object A in thermal equilibrium with object C, and object B in thermal equilibrium with object C, then object A and object B are in thermal equilibrium. Also, we took a look at our 3 different scales of temperature for the ideal gas law that we'll be looking at next. We will be using Kelvin for that. Finally, temperature, we can also say that it's a measure of the average molecular kinetic energy of an object. We have 3 different equations that will get us the kinetic energy of an ideal gas. This first one here is telling us the kinetic energy of a single molecule. The next one is the kinetic energy of a number of molecules. And finally, the last one is giving us the kinetic energy in terms of the number of moles. All right, thanks for listening. Complete your Cornell notes and rewind and review as necessary.